This summer, I'm working with Rich Camilli on manipulator arm calibration through the HUI Summer Student Fellowship. To provide some context to this work, hydraulic manipulator arms are used in underwater environments to collect samples that have a variety of applications. Some of these applications include biological sampling in active volcanic sites, hydrothermal vent sampling, and disaster response. While necessary, collecting these samples often poses numerous technological challenges and constraints, such as limited power for lighting and computation, and limited bandwidth for communication. Automation would help us overcome some of these constraints, and a robust manipulator calibration is an essential first step towards safe and effective automation. In brief, the objective of calibration is to optimize the value of gains and offsets of each of the joints so that we can accurately locate the position of the robot's hand in the environment. Although the relationship seems simple at first glance, the codependence of the joints means that all 12 parameters need to be calibrated simultaneously, which is where the challenge comes in. This summer, I explored two different computer vision-based methods of robot arm calibration, a minimum variance method and a minimum distance method. At a high level, the minimum variance method works by finding the set of parameters that minimizes the variance of the reprojected wrist camera observations. If the parameters are incorrect, observations of the same joint will appear to be disjointed, like in the left diagram. But if they are correct, these points should appear to be the same point, like in the right diagram. However, after testing in simulation, we found that this method is extremely sensitive to even small inputs of measurement uncertainty, and thus was not viable for the calibration task at hand. Meanwhile, the minimum distance method works by finding parameters that minimize the distance between reprojected wrist camera observations and the known position of the landmark. Although a drawback to this method is that it requires at least one landmark's position to be known while the prior method does not, testing and simulation showed that this method should be significantly more robust to inputs and measurement uncertainty. If you'd like to learn more about the analysis, implementation, or testing that went into this project, feel free to stop by my session on August 27th or leave a question below. Thanks for listening.